The project for a 188-ton armored tank became one of the most massive military engineering developments in history. In terms of size, the machine resembled a two-story building, and its mass equaled the combined weight of 10 medium tanks. The armor thickness was planned to withstand impacts from any anti-tank weapons of that period. It was assumed that this machinery could change the situation at the front and ensure the German forces advanced to the east. Adolf Hitler personally approved the concept and insisted on starting production as soon as possible. However, the design had a significant technical problem: excessive weight. In the spring of 1942, the strategic situation for Germany changed. The rapid offensive, which had been effective in Poland and France, slowed down on the territory of the Soviet Union. Tank units faced significant difficulties due to weather conditions and the lack of roads. Soviet T-34 and KV tanks demonstrated higher efficiency than the German command expected. The leadership strove to obtain a new type of weaponry to regain the initiative on the Eastern Front. A meeting was held with representatives of major machine-building concerns, where the task was set to create a practically invulnerable combat vehicle. Project requirements called for armor capable of withstanding direct shell hits and weaponry to engage targets at significant distances without the risk of return fire. No limits on dimensions or mass were established. The main priority was technical superiority. The order went to the Porsche company, whose founder, Ferdinand Porsche, had the trust of the country's leadership. The initial technical assignment envisioned creating a tank weighing 100 tons, which already significantly exceeded the metrics of existing heavy machines, whose weight reached a maximum of 63 tons. The engineering group proposed a project that went beyond the initial requirements. The presented documentation described a combat vehicle weighing roughly 207 tons. The frontal armor thickness was 10 inches, which was comparable to the protection of warships. The sides were protected by plates of hardened steel 7 inches thick, and the roof was over 2 inches thick, providing protection against small-caliber aerial bombs. The plan was to install a 128mm gun in the turret, designed to penetrate armor at a distance of over 1.2 miles. The project received approval as the command calculated on using such machines to break through fortified defense lines. It was envisioned that the machinery could ignore anti-tank weapons and minefields, slowly moving forward and destroying fortifications. An order was given for the urgent construction of the first prototype. The machine received the name Maus, which translates as mouse. After approval, work began on realizing the project. The main technical challenge for the developers became the power plant. To move a mass of nearly 210 tons, an engine of extreme power was needed. Initially, they considered adapting an aviation 12-cylinder Daimler-Benz MB509 unit, but its characteristics proved insufficient. The machinery either didn't move or moved at a very low speed. Later, engineers installed a more powerful Daimler-Benz MB517 diesel engine. It developed 1,200 horsepower, but together with the electric generator, it occupied about 2/3 of the hull's internal volume. This left a minimum of space for a crew of 5: the commander, gunner, loader, driver, and radio operator. In May 1943, a full-size wooden mock-up was ready for demonstration to the client. Leadership inspected the design at the proving ground. The machine's dimensions were significant. It stood 11.5 feet tall, was over 33 feet long, and nearly 13 feet wide. After a series of changes, an order was signed for the mass production of 150 units. But while strategists were planning how to use this new weapon, engineers ran into technical limitations. The first working prototype was finished by late 1943, marking the start of practical testing. Starting the engine and getting that massive structure moving was the critical moment to see if the designer's calculations were right. As the tank started moving across the concrete pad, the surface began to crumble under its tracks. Concrete designed for standard heavy equipment just couldn't take the load, resulting in deep cracks and warped pavement. It became clear that the existing road infrastructure couldn't handle moving something this heavy, creating a logistical nightmare for transporting the planned 150 units. Off-road testing revealed even more problems. On soft ground, the tracks sank nearly 20 inches deep. The machine left deep trenches in its wake, which severely limited its ability to cross terrain. Going uphill, the engine overheated and speed dropped to a crawl. Driving the vehicle proved difficult, maneuvering took a lot of effort, and the braking distance was excessively long. A sudden stop caused the hull to lurch forward significantly due to the inertia of its own weight. The prototype's top speed was 12 miles per hour under ideal conditions. For comparison, the Soviet T-34 could reach 34 miles per hour, and the German Tiger hit 28. Its lack of mobility made the machine vulnerable to more agile vehicles that could fire from a safe distance. Its speed was comparable to marching infantry, which effectively defeated the whole concept of a rapid defensive breakthrough. Major complications arose when they tried to move the Maus tank across a river over a bridge. Even though combat engineers had reinforced the structure beforehand, calculating the load with a safety margin, it couldn't support the machine's weight. When the tank reached the middle, the support beams buckled and the concrete surface cracked, forcing the crew to turn back. Although the bridge didn't collapse, it was declared unsafe and required major repairs. This incident proved that Europe's existing infrastructure simply wasn't built for a vehicle of this mass. Engineers considered various solutions, like building reinforced crossings before every advance, but that would have slowed the unit's movement down to the speed of a construction crew. An alternative proposal to transport the tank in pieces and assemble it on site was rejected as impractical for the field. So the designers came up with a different method, crossing rivers along the bottom. To make this happen, the hull was completely sealed with rubber gaskets on the hatches, and a 26-foot-tall telescopic snorkel was installed on the turret. This provided air for the engine and crew, while exhaust gases were vented through special valves designed to work under water pressure. However, a technical issue came up. Once submerged, the tank's own engine couldn't generate enough electricity to turn the tracks. A creative technical solution was found. A second tank would stay on the bank and send power through a special armored cable to the machine moving along the riverbed. The first tests of this system took place in a river about 16 feet deep. The crew took their positions in the sealed vehicle, which submerged until only the snorkel remained above the surface. The second tank on the shore acted as a generator. The experiment was a success. The machine traveled about 330 feet along the bottom and emerged on the opposite bank. Despite the technical success of the trials, further calculations revealed significant tactical flaws in the method. To cross wide water obstacles, A cable several hundred yards long would be needed, and laying it under combat conditions came with high risk. Furthermore, while one vehicle was crossing, the other had to remain stationary on the bank to act as a power source, making it a vulnerable target. Organizing the crossing for large groups of equipment also remained problematic, as this interaction scheme required a partner for every single tank being ferried across. Eventually, another technical problem emerged: limited range. The powerful diesel engine consumed a significant amount of fuel. On a full tank, the machine could only cover 40 miles on hard surfaces, and on rough terrain, this figure dropped to 25 miles. The actual travel time was limited to about 3 hours, after which the vehicle would come to a standstill. For comparison, a T-34 could cover 190 miles on a single tank, and the Tiger could do 85 miles. Keeping a group of these machines fueled would have required creating a complex logistical system with frequent refueling stops. After inspecting the prototype, General Heinz Guderian characterized the project as grandiose, a description that likely held a touch of skepticism. Guderian was a proponent of mass-producing medium maneuverable tanks. The Mouse project contradicted this concept, representing a slow, heavy design that required significant resources and personnel to maintain. By the beginning of 1944, the question of transporting the equipment to the combat zone became obvious. Railway experts faced difficulties with transport calculations because existing flat cars weren't designed for such weight. A load of over 200 tons was distributed over an area of just a few hundred square feet, creating pressure capable of damaging the track itself. A special platform was developed with a reinforced frame and 14 axles instead of the standard 4. However, even this solution allowed movement only on main lines with sturdy rails and reinforced concrete ties, as ordinary wooden ties could be crushed under the train's weight after just a few miles of travel. Transport speed was limited to 9 miles per hour due to the risk of the train derailing. Delivery from the factory to the front line would take a long time. The loading and unloading process turned into a complex operation involving powerful cranes and special ramps, which was difficult to provide in field conditions. According to military logistics calculations, supporting the combat operations of a single battalion of 10 such machines would require allocating a separate railway branch, dozens of fuel tankers, supply trucks, and a significant technical staff. Initial plans called for the creation of 150 units. At the same time, the strategic situation at the front was changing. In February, the Battle of Stalingrad ended, resulting in the loss of a German force of about 300,000 troops. This event significantly influenced the further course of the war. The Red Army went on the offensive on the Eastern Front. In the summer, a massive tank battle took place at the Kursk Bulge, involving new German models, but Soviet troops held their positions and pushed the adversary back. By autumn, the Dnieper had been crossed and control over Kiev restored. The front line was shifting west, and the German side switched from offense to defense. In these new conditions, the need was not for heavy breakthrough machines, but for mobile equipment for counterattacks and containment. The Mouse project, with a top speed of 12 miles per hour, proved ineffective for such tactical tasks. Its low operational mobility made it impossible to move the equipment in time to sectors where defensive lines were being broken. Work continued on the prototypes at the testing ground. Engineers were trying to eliminate the technical flaws they had found. A modernized engine cooling system was installed. The transmission was reworked, and the suspension was reinforced. However, the main structural problems remained unsolved. Ensuring proper mobility for a machine weighing nearly 200 tons required an engine of ultra-high power, with dimensions that exceeded the capacity of the hull. Physical limitations proved to be a major factor. In June, the situation changed with the Allied landings in Normandy and the opening of the Second Front. Germany was forced to fight on two strategic directions, which led to a dispersion of resources. Industry was working at maximum load, churning out serial equipment. There was an acute shortage of oil, as Romanian fields were subjected to regular bombing. Material and fuel resources became critically limited. The costs of producing experimental heavy vehicles that had mobility issues were deemed irrational. Albert Speer, the Minister of Armaments, presented a report with the calculations. The cost of a single Maus was equivalent to 5 Panthers or 8 Panzer IVs. The resources needed to build 150 super heavy tanks would have been enough to produce over 1,000 medium tanks capable of influencing the course of combat. Speer insisted on winding down the program and redirecting capacity to the production of proven equipment. The country's leadership, specifically Adolf Hitler, did not agree at first, banking on the potential of the newest types of weaponry. By the autumn of 1944, the Red Army had reached the borders of East Prussia. Romania, Bulgaria, and Finland had exited the war. Soviet troops were right near the German borders. In the west, the Allies had liberated France and Belgium, preparing to enter German territory. The Third Reich's strategic position was deteriorating, casting doubt on the feasibility of long-term projects. The priority became arming the army in the shortest possible time. In November, an order was signed to completely stop work on the Maus project. All resources were directed toward the production of serial tanks and anti-tank artillery. The two built prototypes remained at the proving ground in Kummersdorf, near Berlin. There were plans to use them for the defense of the capital in the event of a direct threat. However, no effective tactical application for such machines could be found. The project was effectively closed due to its incompatibility with the real conditions of warfare. The second prototype was fully equipped with a turret and gun, while the first utilized a concrete weight simulator, as they did not have time to install the real turret before the program shut down. A group of engineers and mechanics continued to conduct trials to gather technical data, despite the project's suspension. The tanks were tested on the range, specs were measured, and systems were checked. Firing tests were conducted with the main caliber. The 128mm gun demonstrated high accuracy and power, yet the carrier's low mobility limited the weapon's effectiveness. The winter of 1944 to 1945 was difficult. Soviet troops were advancing rapidly through Poland toward the German border. The German army was retreating, abandoning defensive lines. In the west, Anglo-American forces were fighting in the Ardennes. Territory under German control was shrinking. In January, the Vistula-Oder offensive began. Soviet tank units broke through the defense and pushed deep into Germany. In a few weeks, they covered the distance from the Vistula to the Oder, which is nearly 310 miles. The high pace of the offensive made it difficult for the German command, to organize new lines of defense. Soviet tank formations and heavy machinery pushed forward, bypassing pockets of resistance. By the end of the month, advance units were about 43 miles from Berlin, putting the Kummersdorf proving ground in immediate danger. The German command issued an order to evacuate valuable equipment and destroy anything that couldn't be moved. Engineers were ordered to blow up both super heavy tanks to prevent them from being captured by the enemy. Intelligence already knew about these machines and planned to seize them for analysis, while the Germans were well aware of the technological value of the prototypes. Explosives were planted in both vehicles. The second tank was critically destroyed. The explosion damaged the hull, the turret was knocked off its ring and tilted over, and the running gear was torn apart, turning the machine into a pile of scrap metal. Things were different with the first prototype due to a shortage of explosives, so the charge turned out to be weaker than necessary. The blast damaged the running gear and the engine, but the hull remained relatively intact. There was no time to replant the explosives because Soviet reconnaissance groups were already appearing in the area. On April 21, 1945, combat engineers entered the testing grounds, which the German personnel had already fled, leaving behind documentation and equipment. Among the ruins of the buildings, the troops discovered the remains of two massive tanks. The sheer size of the hardware and the thickness of the armor caught the soldiers' attention as they conducted an initial inspection of the found machines. Military intelligence representatives reported the discovery to leadership, after which an order came down to retrieve the hardware. The interest in these objects stemmed from the chance to study design solutions in tank building, metallurgy, and engine construction, as these were unique specimens of their class. The transport process required solving some difficult logistical problems. Specialists assembled one complete vehicle from the wreckage of the two prototypes. The intact turret from the second unit was mounted on the less damaged hull of the first. After replacing the tracks and partially repairing the engine, they obtained a hybrid model that offered insight into the German engineering design. To move it, they used a special 14-axle German railway platform designed specifically for this type of equipment. Because of damage to the railway lines, the train moved at a slow speed, bypassing unreliable bridges. The journey to the Kubinka proving ground, designated for testing captured equipment, took nearly 2 months. Movement took place during daylight hours under guard, with regular stops to check the tracks. In the summer, the Maus arrived at the testing grounds in Kubinka. Engineers carefully measured the machine, photographed the details, and disassembled the accessible components and assemblies. A series of driving tests were conducted, which confirmed the Germans' calculations were correct. The tank reached a speed of about 12 miles per hour and guzzled a significant amount of fuel. The armor was also tested by shelling it with captured anti-tank guns. The rounds ricocheted without causing damage, which explained the German leadership's high expectations for this project. However, the designers reached the same conclusions as their colleagues. The concept of super heavy tanks was a dead end. Low speed, massive fuel consumption, and problems with transport and maintenance made such machines unfit for real-world operating conditions. Other heavy tanks were being developed at the time, but even the massive IS-3 weighed 50 tons, which was more than 4 times lighter than the Maus. Tank building moved toward creating balanced machines with an optimal ratio of protection, firepower, and mobility. For several years, this giant tank sat at the proving ground as a testament to the technical ambitions of the war era. Periodically, it was shown to military delegations, used as an example of exactly which decisions to avoid in tank building. Foreign engineers examined the mouse, noting details and photographing the specimen. The machine sparked interest in the level of engineering work, but at the same time raised questions about the viability of the concept itself. By the early 50s, the tank had definitively turned into a museum piece. The engine had failed, the rubber components of the running gear had lost their properties, and the interior smelled of oil and rust. The mouse was moved to its permanent home at the Kubinka Tank Museum, where it took its place among other captured vehicles. It was displayed alongside tigers, panthers, and Ferdinands, armor that had actually been used in the past war. Museum visitors often lingered near this exhibit the longest. The tank's dimensions remained impressive even decades later. People walked up to tracks that stood taller than a man, inspected the thick armor, and tried to get a look at the interior through the viewing slits. Tour guides would tell the story of how this object was created, explaining why it was absent from combat, and using the mouse to demonstrate how raw technical power, without a strategic basis, becomes ineffective. Subsequent generations of engineers studied this tank as a visual guide to design errors. The design held quite a few interesting technical solutions: an electric transmission system, hull sealing for underwater travel, and powerful weaponry. However, all these achievements were negated by a fundamental flaw. The tank was simply too heavy for its time. Technology in the 40s didn't allow for the creation of an engine with enough power that was still reasonable in size and fuel consumption. The designer's attempts to bypass physical limitations proved unsuccessful. The story of the mouse became a textbook example for tank builders around the world. When the American M103 heavy tank was being developed in the 50s, and engineers were working on Object 279, experts on both sides considered the lesson of the German giant. Both projects remained as technical documentation or existed only as single prototypes. The development of armored forces in that period shifted toward creating medium and main battle tanks weighing 40 to 50 tons, capable of combining the proper level of protection, firepower, and mobility. The only surviving mouse tank now resides in a museum, demonstrating the result of the disconnect between theoretical planning and practical realization. This machine, which became the heaviest tank in history and required significant production resources, was never actually used for its intended purpose. Its guns were never turned against an enemy, its tracks never breached defensive lines, and its armor never faced fire in real combat conditions. The 188-ton structure has been preserved as a museum exhibit, illustrating a specific stage of engineering thought. Historical experience shows that the advantage in conflicts is not provided by the sheer scale of a single weapon, but by its overall efficiency and suitability for tactical tasks. Studying such technical solutions allows for a more detailed analysis of the specific features of military-industrial development during World War II.